You ever look at your phone or your TV and just marvel at that incredible screen? We see these brilliant, vibrant images, but we completely miss the microscopic world of engineering that's making it all happen. Well, today, we're going to pull back that curtain and look at the unseen genius in your screen, the thin film transistor, or TFT. So let's get right into it. We usually give all the credit to the OLEDs themselves, right? The organic light-emitting diodes. And yeah, they're amazing, but that's only half the story. The real secret to that perfect picture isn't just what glows, but how it's told to glow. I want you to imagine millions of tiny individual light bulbs on your screen. To make a picture, every single one of them needs to be told exactly how bright to be, thousands of times a second. They need a control system, a tiny little brain for every single pixel, all working together perfectly.
And that is our star of the show, the thin film transistor. A TFT is basically a microscopic switch, or maybe think of it like a valve, that's layered onto a big sheet of glass. Its one job is super critical: control the exact flow of electricity to its own little OLED pixel. If you get this right, you get a perfect image. But if you get it wrong, well, the magic is gone.
So if you're an engineer, the first huge challenge is figuring out what to build these millions and millions of switches out of. This decision is what I like to call the great silicon dilemma, and it really sets the stage for everything else. The material has to be a semiconductor, and the number one choice is, of course, silicon. But, and this is a big but, not all silicon is the same. The way the silicon atoms are structured is going to determine the performance, the cost, and just how hard the whole display is to make. You've basically got two main options: amorphous silicon and polysilicon. Okay, think of amorphous silicon like a big pile of jumbled up marbles. The atoms are a total mess. Electrons move really slowly through that chaos. Polysilicon, on the other hand, is like those same marbles arranged in perfect orderly lines. Electrons can absolutely zip through it at incredible speeds. The catch? Making the messy version is easy and cheap. Creating those perfect crystals, that's really, really hard and expensive. Now for OLEDs, they are super demanding. They need a lot of current and they need it fast to get those bright, vibrant colors. So there's really no contest here. You have to have that high electron mobility, the pure speed of polysilicon. So engineers chose the harder path, which, of course, leads to the next big question. How do you possibly forge these perfect silicon crystals on a simple sheet of glass? This is where the process starts to sound like something straight out of science fiction. Seriously, we're talking about using incredibly powerful lasers to change a material at the atomic level, all without destroying the fragile glass it's sitting on. So here's the fundamental problem. To turn that messy amorphous silicon into orderly polysilicon, you have to get it hot, like over 700 degrees Celsius. But the glass it's built on, it starts to get soft and warp around 670 degrees. You can't just stick the whole thing in an oven, you just get a melted, useless mess. The solution is just brilliant. What if you could heat only the silicon and do it so fast, I'm talking nanoseconds, that the heat literally doesn't have time to spread to the glass underneath? This process is called excimer laser annealing, or ELA for short. A powerful UV laser fires this incredibly short, intense blast of energy. It hits that thin film of amorphous silicon and instantly melts it. Then, as it cools down in the moments right after the blast, it reforms into that beautiful, orderly, high-performance crystal structure we call polysilicon. It's just incredible. So what does this actually look like in the factory? First, they lay down a super thin layer of that messy, amorphous silicon on the glass. Then the magic happens. The excimer laser scans across it, zapping it with pulses and turning it into high-performance polysilicon. After that's done, they carefully build the rest of the transistor in layers on top. And finally, they pattern a clear electrode to connect our new TFT to the OLED pixel it's going to control. But, and in engineering, there's always a but. This powerful laser process isn't perfect. Tiny little fluctuations in the laser's energy from one pulse to the next mean that not all the crystals form in the exact same way. So you end up with millions of transistors that are all slightly different from their neighbors. And that, well, that creates a huge problem. So you solve the material problem, you solve the manufacturing problem, and what happens? You create a uniformity problem. The solution here is just another layer of pure genius. You make the circuits smart enough to correct their own flaws. This visual problem actually has a name: Mura.
It's a Japanese word for unevenness. On a screen, it looks like blotchy, cloudy patches. You usually see it on solid colors. It's the direct result of those slightly different TFTs sending slightly different amounts of current to their pixels, even when they're all supposed to be identical.
I mean, think about that challenge. It's massive. You can't go in there with a tiny tool and fix each transistor one by one. There are millions of them, and each one has its own unique little error. The fix has to be automatic. It has to be built right into the pixel itself. And that's exactly what they did. Engineers designed what are called compensation circuits. Instead of just a simple switch and a driver, they added a few more parts to every single pixel. This extra little bit of circuitry gives the pixel the ability to diagnose and then fix its own errors in real time. So here's the basic idea put simply. During a quick little setup phase, the pixel circuit basically takes a reading of its own main transistor to measure its specific flaw. It then stores that unique error value. Then, when the actual video signal comes in, the one telling the pixel how bright to be, the circuit automatically adjusts that signal to cancel out the error it remembered. The result? The final current sent to the OLED is perfect, and that ugly mirror just disappears.
But the engineering puzzles just keep coming. For example, you need pixels to be completely off to get those perfect inky blacks. So engineers build special structures into the transistor to stop tiny bits of current from leaking through. But here's the trade-off. The better you make it at stopping leaks when it's off, the more it also resists current when you want it on. It is a constant, delicate balancing act.
So this constant battle, right? This trade-off between performance and uniformity and how hard it is to make and cost, it pushed scientists to look for something totally new, beyond silicon. And that led them to a whole new class of materials that promised to solve a bunch of these problems all at once. For years, the choice was basically between slow but uniform amorphous silicon and fast but non-uniform polysilicon. What if you could get the best of both worlds? The high performance of a crystal, but with the simple, uniform manufacturing of the messy stuff. Enter oxide semiconductors, and the most famous one is IGZO. That stands for indium gallium zinc oxide. Now, the reason it works so well is the key. Silicon needs those atoms lined up perfectly for electrons to flow. If they're not in a perfect crystal, performance just dies. But IGZ, its atoms are like big spheres. So even when they're all jumbled up and messy, these spheres still overlap enough for electrons to move freely between them. And what this gives you is pretty much the best of all worlds. You get really high mobility, almost as good as polysilicon, so you have all the power you need. But you can make it using a simple, cheap process, just like amorphous silicon, which gives you amazing uniformity. It also has naturally low current leakage, and, this is the big one, it's scalable. IGZO is the technology that finally let companies build those massive, beautiful OLED TVs we all love today. So, from a fundamental choice of a material, to forging crystals with lasers, to building circuits that literally heal their own flaws, the screen you're probably watching this on is just a chain of brilliant solutions to incredibly difficult problems. It really makes you wonder, if the hidden intelligence inside our displays is already this sophisticated, what amazing things will it let them do next?